This presentation will be on computer memory. We divide logic circuits into two categories, combinatorial and sequential. A circuit is said to be combinatorial if its output is determined solely by its inputs at a given instant. And so we know we can write the outputs depending on those inputs as a truth table, and we can then build it based on sort of a sum of product or product of sums approach. An example would be addition. So the numbers that we wish to add are the inputs, and then the output, the sum of those two numbers, depends only on those inputs at that given instance. A circuit is said to be sequential if it depends in some way on its history. An example of this would be a counter. So the input to a counter will be to telling it to increment, but what it will increment to depends on what it was previously. So it depends on its state. So if the counter was 34 and you tell it to increment, it will become a 35, and so on. And so it depends on its history or on its state. And so we need to know what its current state and not just the inputs. If the sole purpose of a circuit is to hold ones and zeros, to do the holding, then such a circuit is called memory. If we consider the smallest unit of memory, something that will hold a single bit, a high or low, that is called a flip-flop. If we collect together a bunch of flip-flops to sort of work as a unit, then they are known as a register. And what they are said to hold is a word. It may be a number, it may correspond to a letter. We don't know. That depends on some other piece of information will determine how to interpret the bit string, but the bit string is held by a register, and it is simply generically referred to as a word. If we have a collection of registers and we make that collection of registers addressable, we've seen how to do this with the decoder, then we have memory, or RAM, random access memory. RAM has not only the addressable set of registers, but it also has some special purpose registers that are involved in its use. One of them is the memory address register. So the memory address register is a register. It's going to hold values, and what it holds is the input to the decoder. It holds the address, hence the name memory address register. And it feeds into the decoder, so it supplies the address to the decoder. The job of the decoder is to select the register from the set of registers that's at that particular address, and then that data on the other side gets connected to a memory data register, an MDR. So there are special purpose registers, the memory address register and the memory data register, on either side of dealing with this sort of large set of addressable registers that make up altogether random access memory. So if you're familiar with the concept of an array from programming, then RAM is somewhat like that, in that you have values associated with locations. And so if you know the location, you can know the value. If you're at the sort of lowest level, if the values you're considering are in physical memory, then you must address them absolutely. You must know their precise location within the memory. But when you're working at a higher level, you might be working with more of a relative address, where you say, I know where one thing is, and then I am so far from it. So I know my relative address relative to something else. And so this is how, again, going back to arrays in programming, that they are a type of relative addressing, where the array itself will be given an address, and then the index within the array will be a type of relative addressing. And so I will say I am so far from the base address for the array. And so the same way that we understand when we know how a decoder works, why addresses start at 0, we can also now know why array indexing starts at 0. Now we're going to return to the simpler units, the flip-flop and the register, and ask what actions and what properties are needed to be able to call a circuit memory. And so basically they're going to be two, writing and reading. So we need to be able to set a value, to put a value into the flip-flop to make it high or make it low. So if we're down at the flip-flop level, then we are writing to it. And if we write a 1, we're going to call that a set. If we write a 0, we're going to call that a reset. And then we also have reading the flip-flop to get its value. And that is just going to be reading. Now we always make the memory to understand reading and writing and keep them straight in our head. You should remember that when you're writing sentences about memory, memory is not the actor. Memory is sort of acted upon. So grammatically, memory should be like the object of your sentence, and the CPU or something else would be the subject. So the CPU will write to memory. The CPU will read from memory. Memory is always acted upon. One of our examples of a sequential logic circuit was a counter. And so now let's think about what happens with a counter. You give it an input that tells it to increment, and it takes its state, say 34, and makes it 35. But if the state is still saying increment, then how do we know that the 35 is not going to become a 36 and a 37 and a 38? Well, when we have sequential logic, we also have to introduce the concept of the clock, that we will respond to our input at a given time. And so we have a computer clock, and we have a binary system. So as far as we're concerned, a binary clock is something that oscillates between highs and lows, between zeros and ones. And then we're going to just focus on memory as a type of sequential circuit. Our flip-flops are going to have a number of kinds of controls. One control will be whether or not to write, and then there'll be timing controls, when to write, and then there will be data controls, what to write. And sometimes we will find the control and timing are in some way combined. Talking about memory can be quite confusing, so we want to make some distinctions. The first is between storage and memory. So storage is your hard drive or your solid state drive. It comes in sort of terabytes. It's quasi-permanent. It's non-volatile, meaning that if the power goes off, the stuff in storage is still there. It's still safe. Memory is a temporary thing. It's volatile. If the power goes out, what was ever in memory is lost. And it's what I'm working on right now, and it usually is measured these days in gigabytes. One of the reasons for the confusion is that what I'm working on now is changing in the course of time, and so one is constantly swapping in and out what is in storage and what's in memory. Another thing within memory is ROM versus RAM and the roles they play in the computer. And also within RAM, there is DRAM and SRAM that comes up in the way they are used. And we'll also, in that discussion, talk about memory versus cache. So we've got a bunch of distinctions to make. ROM is read-only memory, as the name suggests. Of the two actions of memory, reading and writing, this kind of memory you only read. So in the strictest sense of ROM, it's written by the manufacturer. It comes completely written, and you will only, as a user, ever read it. It is non-volatile. It does not depend on a source of energy. If the computer is turned off, then the ROM is still there. That information is permanent. So ROM is read-only, and it doesn't change. So one thing you use ROM for is any part of code that's not going to change you would put into ROM. ROM is also non-volatile, so it's there when the computer starts. So one thing that you will put into ROM is the booting code of the computer. So the computer stopped for whatever reason, it lost anything that was in memory, but you start it back up and it's going to grab the boot code is going to still be there because it was in ROM. And you'll put it also in laser printers. You might put your default fonts there. So anything that you sort of, some bare minimum instructions that or information that you always want your computer to be capable of, no matter what else happens, that's the stuff you put in ROM. Another use of ROM is in what's called microcode. It's the lowest level of instructions. So you might put in RAM an instruction to perform an addition, but the actual things the computer has to do to perform an addition will be in ROM. So you will tell the computer when you want to use addition and what data you want to perform addition on. That will be in RAM, but the actual part of the computer that knows what addition means and performs it, that never changes, so that would be in ROM. And another place is in what's called the BIOS, the basic input-output system. So this basic interactions with the I/O, the peripherals, again, is something that changes quite rarely, if at all, and so can be in ROM. So as ROM developed, we moved away from the only the manufacturer writes ROM, and then our next level is what we call PROM, Programmable Read-Only Memory. And so this is a type of ROM where the purchaser, the consumer, the user can write to it, but it is sort of written to once. So another term for it can be write once, read many. Sometimes it will be called a worm. And so it's like a CD-R. You have some special way of burning it, so it's a blank CD, and so you will write something onto it, but after that it is only read. So PROM, Programmable Read-Only Memory, was written to once. The next stage in the evolution was EPROM, Erasable Programmable Read-Only Memory, and then there was some special process for erasing the content of the ROM, and then it could be rewritten. And so originally this was some special outside of the computer process, so you had to expose it to ultraviolet light, but there was a way for you to rewrite, to erase and rewrite. And then the next stage was EEPROM, Electrically Erasable Programmable Read-Only Memory. And so now the erasing was done by an electronics means, so you don't have to remove it from the computer. Maybe it's a larger currents or larger voltages for the writing than for the reading. Now, as the alternative to ROM is RAM, Random Access Memory. So let's see what the term random access means. Random access refers to how the data is accessed, how it is read. And so we distinguish between sequential access and random access. So sequential means you go in some particular order. So the example for that is some kind of tape. And so you have a cassette tape or a videotape, an old-fashioned way of recording programs. And minute 1 is in this part of the tape, and minute 2 is in the next part, minute 3. And if you want to, you can fast forward or rewind, but you have to move through all of the locations to get to where you might want to be. Random access allows you to sort of jump all around, and so when we have our addressing scheme, when we are using the decoder, then you can go to that address. And so as far as the device is concerned, it's maybe random. In your mind, it has your code has some logic to it, so you don't think of it as random, but as far as the device is concerned, it's random. You provide the address, you go to that address, it doesn't matter. And so actually, ROM is RAM in that ROM uses a decoder and is accessed randomly. ROM is not sequential, ROM is random access. But when we make the distinction between ROM and RAM, there is more to the distinction than just the names imply. When we say RAM, we mean a volatile kind of memory, a memory that will be lost when we lose the energy source. So it's distinct from ROM, even though the name might not suggest so. As opposed to ROM, RAM is both written and read, and it is also volatile. It will lose the information written if the power were to go out. Within RAM, we have two main types of SRAM and DRAM, static RAM and dynamic RAM. And don't go by the normal feeling that you have for these adjectives. Remember that in memory, the purpose is to hold on to a state, to remember some history. And so in that case, static is good and dynamic is bad. So the dynamic, you've written, say, a 1, and then that 1 is being lost and will need to be refreshed. And the good thing about static RAM is that it does not need this refreshing. And so it's going to be faster, but it's going to be more expensive, whereas DRAM, dynamic RAM, is slower but cheaper. Now there's a pretty long history of various types of DRAM, which is going to sort of cut to the chase into the more modern versions. So all modern DRAM is known as synchronous DRAM or SDRAM. And synchronous means sort of how the memory works in conjunction with the computer's clock, the processor's clock, and the various buses in the processor. And then all of the sort of evolution of DRAM is about sending a lot of information at once, dealing with what in the early history were known as bursts, sending a lot of information at one time. And one of the more modern inventions is the DDR sort of family. So the first one was Ddrsd Ram, double data rate, synchronous dynamic random access memory. And so you have a clock, and it's handling information being passed on a bus, and a clock has what is known as an edge. So a clock, a binary clock, is 0 and 1, 1, so 0 to 1, 1 to 0, back and forth. The change from 0 to 1 is known as an edge, and 1 to 0 is another edge. And DDR, double data rate, means that you did something on both edges. And then DDR2 and DDR3 in more recent history, these are doing sort of multiple things on an edge. So it's just a matter of speed and coordination with the clock and the buses. In our distinction between RAM and ROM, we said that RAM was volatile, then it lost its information if the power went out, and that ROM was read-only. Now let's blur that distinction. So within RAM, you can have what's called non-volatile RAM. So this is RAM that is not going to lose its data if the power goes out. So you're sort of giving the memory sort of its own little battery supply that will allow it to hold on to information. It won't be permanently or semi-permanently like Prom, but it will give you a chance sort of while the battery is in play, holding on to the information to get it written to something, to a disk, to storage. And so this is a distinction, so that RAM typically we think of as volatile, but we can make it a little less volatile. So non-volatile RAM doesn't mean that it's not volatile at all, but it's less volatile than normal RAM, and so it buys you a little time to do something. So now let's blur the distinction from the other side. The problem with ROM was that you didn't write it, and then we went to Prom and EPROM and EEPROM so that we could finally write it and somewhat easily. And flash memory is a version of EEPROM that's sort of even easier to write to. And so then it became, as we know, sort of flash drives and solid state drives. So we have this permanent, so non-volatile version of EEPROM, but it's easier to write to than older versions of EEPROM. So it's become it's ROM, but it's relatively easy to write. And so again, we're blurring the distinction. So we made a distinction earlier between SRAM and DRAM, static RAM and dynamic RAM, and we want to see how that comes into play when we have cache. So cache is a generic term, and it's used for making a guess about some data that you will need and then putting it in a place that it's easier or more quickly accessed. And then you have generic terms also in terms of this guessing game of a cache hit is a correct guess and a cache miss is an incorrect guess. So you might cache a web page. So instead of going out onto the internet and fetching a page from the web server, you might look and see if you have a copy of that web page already on your computer, if perhaps you've accessed this page before. So that is the idea of caching. Thinking of things that you might want to use in the future and putting them in the convenient place and grabbing them. But that's not the level of cache that we're talking about here, because we're talking about SRAM and DRAM. And so we are talking about memory cache, and memory cache is standing in for memory. So memory, what we call memory in a computer or RAM, is DRAM. And then we will take a subset of what's in memory. And so we think of memory as what we're using, but cache is what we're sort of really using. And so we take a subset of what's in memory and put it right onto some memory that we have on the processor, and this is known as cache. And that uses it's right on the processor, so it's faster than going to memory to the DRAM, which are separate chips. And also, so it's right on the chip, so it's faster, but it also uses SRAM, which is the faster kind of memory. And then it's even more confusing than that. There are different levels of cache. So it used to be there's L1 cache and L2 cache, and originally L2 was on a different chip, but now it's on the processor. So we have these different levels of cache, but they're all standing in for memory, which is on a different chip and uses a slower type of memory. And as we say, cache is complicated. So the cache is a faster version of memory that's on the processor standing in for the RAM. And RAM is something that you can not only read, but write. So now you are working with the cache and it comes time to write to it. And the question comes up, should I just write to the cache or should I write to both the cache and the memory? And eventually I'm going to have to write to the memory, but the question is when. And so there's different policies for this. There's a write back and a write through. And so write through means as soon as you're changing the cache, you will change the memory. And that sort of slows you down because you're dealing with memory, which is slower. Whereas write back says, I'm going to write to the cache, but I'm not going to write to the memory right away. I'll do it when I need to. So some people will ask, if you have SRAM and DRAM, if you have this faster memory and this slower memory, why don't you just use the faster memory for everything? So let's talk about the pros and cons of SRAM and DRAM. So the pros of SRAM is that it is faster and it's simpler. It doesn't require the refreshing, so you're not slowed down by the process of refreshing, and it's simpler. You just simply don't have the process of the refreshing. The cons of SRAM are its size. It's a more complicated circuit, and so it's going to involve more transistors than DRAM, and it's going to take up more space on a chip. It's also going to cost more, so if you want the same amount of it, you're going to have to build a bigger, more complicated chip. It's going to cost you more. Also, it uses a constant current. So the DRAM involves a capacitor. You charge up the capacitor, and so there's only current while charging or discharging the capacitor. But SRAM involves a constant current, so it's got the potential that it's going to use more power and generate more heat than DRAM. Let's consider one more topic that can be part of memory. So we are writing to some register, some data that we want to hold for a while. And so we are writing binary information, ones and zeros. And in addition, we can add an error detection bit. And one version of error detection is parity. And so we can have odd parity or even parity. And so let's say odd parity. And so between the data stored and the parity bit, you want the number of ones to be odd. So in that first row where there were 0 ones, you make the parity bit a 1. In the second and third row where there was 1 1, it was an odd number of ones already, so you make the parity bit 0. In the last one, when there are 2 ones in the data, you will make the parity bit a 1 to make it 3, to make it an odd number. And the purpose of this is for, as we say, error detection. So you put that when it comes time to write, you not only write the information, but you write the parity bit. And then when it comes time to read, you not only read the information, but you read the parity bit. And then you can test with your own parity calculation and see if you agree if the parity is odd. And if the parity is not odd, then you know that some mistake has occurred. One issue with parity is you have error detection, so you know that some bit was flipped, there's some problem, but you don't know which bit, and so you don't know how to necessarily fix the problem. You just know that there is a problem. So that brings in the idea of vertical parity, so that you can do a sort of a parity calculation in both rows and columns, and then when you do this sort of larger calculation, you can find out, like, if there's a parity violation, if there's a problem in this row and that column, then you have identified the problem bit and you can fix it. This raises the distinction between error detection and error correction code. So our original parity just found that there was an error, and so that is error detection. And CRC and checksums and parity, these are all versions of error detection. The vertical parity was a version of error correction, and that we could figure out which bit was wrong. And another version of that is Hamming code.